Good morning, folks. Here we go. Today's Tuesday, not Thursday. That's weird. Um, November 10th for us. Supposed to be a little bit snowy today, I think. That's crazy. I don't like it yet. So today what I want to do is I want to talk you through drag force a little bit more and terminal velocity. We're also going to talk momentum and a concept called impulse. Um, and we'll do our first named problem, which is a ball and bat problem. And then I'll get you some time for practice and stuff like that. Um, so here's what we got for you. All right. So um, I want you to try these out. So how much does a 75 kilogram human weigh near the surface of Earth? Now, remember for this one, when we talk about weight, that's our force of gravity. All right. So force of gravity, that just means the mass times. So that mass, let me get a pen here. So that mass there times the gravitational acceleration, which is 9.8. So we see it's 735 newtons. All right. That's just their weight. Okay. So the human goes skydiving, spreads their arms and legs like a flying squirrel. When they achieve terminal velocity of 54 meters per second, right? That's about 120 miles an hour. What is the force of air drag? No, the key piece here is that when they achieve terminal velocity, remember, means that there's no more acceleration. Our forces are all balanced. The downward force of gravity is balanced by the upward force of the air. All right. So whatever our downward force at that point is going to be equal to our upward force. So in this case, we should see that they're the same. All right. So now the human gets all streamlined, head first dive, blah, 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 hits a new terminal velocity, all right, of 90 meters per second. So just about 200 miles an hour. Okay. Now what is the force of air drag? Again, because they're at terminal velocity, right? In between this 54 and 90, the forces are unbalanced, 100%. Okay. That's not what we're asking. We're asking when all of a sudden they hit this new terminal velocity here. Okay. And terminal velocity is the key term here. Once they hit that new terminal velocity, their force downward, again, the gravitational pull from the Earth, is going to be balanced out by the air drag or the air pushing back upwards against it. Okay. So what we know here is that if the air is equal to the gravity, then it should be 735 again. All right. Their weight will always be the same there. All right. So when a falling object achieves terminal velocity, the drag force of the air on the falling object is the same as the object's weight. All right. Remember, as it achieves terminal velocity, its acceleration is zero. It's completely balanced. I know that seems very, very odd because it's moving at a high rate of speed, but it is acceleration of zero. Because there's no acceleration, there is no unbalanced force. Our forces are balanced. When our forces are balanced, we just have to figure out what forces are at play. At that moment in time, the downward force is from gravity or the weight. The upward force is from the air. Those two then equally cancel each other out and allow us to be at nature's cruise control, which is terminal velocity. Okay? Let me know if that doesn't make sense. Let me know if you're still a little bit sketchy on that one. All right? But basically, if we pull in the previous example, if we pull the parachute and we're going 5 miles an hour at terminal velocity, the force of air pushing up against it would be 735 newtons. Okay? If all of a sudden we were, Felix Baumgartner and we were going 833 miles an hour, at terminal velocity, the force would be 735. Okay? All right. Momentum. Momentum is something that you probably experienced in your life, right? Momentum takes into account both velocity and mass. So when you're driving up to that stop sign or a stoplight, and all of a sudden that thing turns yellow and you can't get through it on the yellow, so you have to stop immediately, what you feel is momentum, right? Your body wants to continue going forward, right? Very similar to inertia. Um, but now with momentum, it's a little bit different for us. Okay. The symbol is P. Um, the reason why momentum is labeled as P is they used to call it progress, which is the quantity of motion in which a body proceeds in a certain direction, which makes sense, right? You think about it, that stoplight, your body wants to continue going forward. All right. Now, the way that we can stop that motion is obviously with seatbelts, airbags, if we got into an accident and stuff like that, right? But progress becomes a big deal for us. How much momentum do we have? How much kind of, force over time is that going to have for us as well? All right. Formula for momentum. So now make sure that we take this formula here and that we circle star highlight that, put that in our list of stuff. P equals mv. Again, P is momentum. M is our mass in kilograms. V is our velocity in meters per second. So momentum is measured as kilogram meter per second. All right. Or we can also have it be Newton seconds, which I'll show you in a little bit. All right. Those are our two. Those are synonymous with each other. Those are the two that work for us. Okay. So Cal's truck has a mass of 2,000 kilograms, and he is driving at 30 meters per second in the positive x direction. What is the momentum of Cal and his truck? So if our mass is 2,000 kilograms, which is perfect, and our velocity is 30 meters per second, what we're going to do is multiply those two together, right? And we're going to see that he has 60,000 Newton seconds or 60,000 kilogram meters per second. All right. Either one of those labels, absolutely perfect for us. Okay. So that's kind of the concept behind it, is that we're going to see this as how we can calculate how much momentum a vehicle would have or an object. Impulse. Okay. Now, impulse, all right, impulse is a change in momentum. So momentum is just a singular instantaneous measurement for us. Impulse is actually a change. How does this momentum start to become different? All right. So we see delta P equals F, or sorry, let's see if I can do that. Nope, I can't. Okay. F delta T, right? So again, circle star highlight that one. This one, I don't know if you need to do as much. Okay. Another version that I would write down is delta P equals M delta V. My University of Phoenix game isn't online today, is it? I can't draw very well. So those two, again, are going to be really, really crucial for us, okay? Just think of impulse as this change in momentum, all right? So we ask, which requires more force? Changing a person's speed from 5 meters per second east to 10 meters per second east in 2 seconds, or changing a person's speed from 5 meters per second east to 10 meters per second west. Now, directionality becomes super important here, all right? Because in A, the two are going the same direction, those velocities will actually just subtract as well, okay? Meaning that it'll be from 10 to 5, the change in velocity is only a 5 meter per second change, all right? Not a huge deal. Notice in B, though, we're going 5 meters per second east and 10 meters per second west. We completely change direction. So what that means is that instead of it being a 5 meter per second change, it's actually one of those is negative. So we would go 10 minus a negative 5. It actually is 15. So if you think about it, which one should require more force? The 15 in 2 seconds versus the 5 in 2 seconds. So it should be the bottom one. A change in direction usually results in more force required in order to do that. Think about it. You got to stop and then get going back again the other way. All right. All right. So here we go. Ball and bat problem. So a pitcher throws a 47 meter per second fastball over the plate. It's about 105. The batter then hits it right back to the pitcher at 53 meters per second, which is about 120 miles per hour. If the ball has a mass of 0.146, it actually does. That's the mass of a baseball. What is the impulse of the baseball? Now, here's what I want you to think about. Okay, when we look at this problem, directionality matters so incredibly much. The pitcher is throwing it that way. The batter is hitting it that way, right? Because they're hitting in opposite directions, this impulse should be huge. We're going from 105 miles an hour that way to 120 miles an hour that way. All right. Now, it doesn't say how long this takes, which is good, because if this were to be experienced by a human body, honestly, folks, we would be done. It'd be bad, right? Think of it. You're driving 105 miles an hour this way, and in an instant, boom, you're going 120 that way. I mean, that's a huge amount of change in momentum for us, okay? So when we look at this, again, impulse is a change in momentum. So our change in momentum, we're going to take the difference in masses, all right? So what we're going to see here is we're going to take that mass. Now notice the 47 meters per second, I made that the opposite one, okay? Because I'm saying that from the perspective of the batter, we're going to see this thing go that way, all right? So because it's opposite, this change in impulse actually is incredibly huge. That 53, excuse me, has to be added to the 47. By doing that, we see it's 100 meter per second difference. All right, that's impulse. All right, here's practice 4-1 for you. We will, this is due by the end of the day for us. So go ahead, I'll have an answer key up here for you to be able to look at too as you see it, and then run that and try that out. All right. Hope you have a great day. If you got questions, as always, let me know. Talk to you. Bye.